And that is the story, the initial story of magnetism. And then the next step is the magnetic field due to a current. Now we have enough time. I think we should do a little bit of this today. And we said that magnetic fields were generated by currents at the beginning of all of this, and QV in effect is a current if you think about it that way. So to compute electric fields, we had our differential charge element, our dq, which was typically equal to, say, lambda ds or something like this. All right? And if we were to try the same thing here, we have to figure out how we're going to do that. For B fields, lacking monopoles, the conceptualization is more difficult. Without a proof, we have dV is equal to mu naught over 4 pi IDS sine theta over r squared. Now, mu naught is called the permeability constant. Now, because there's a B in there, it reminds me of magnetic fields, whereas the permeability constant in the case of electric fields is different. Okay. More formally, dB will be mu naught over 4 pi IDS cross r over r cubed. And this is known as the Biot-Savart law. And that's your fundamental principle for magnetic fields. Now, if we are clever in how we do this, and in this case you'll notice that we're not using areas, but rather lines. If we're clever how we do this, we can obtain a way to compute at least some magnetic fields with comparative ease. Okay, so we've got a fair bit of stuff here. I don't know if I want to start that today, but I will do this. For a straight wire, the magnetic field, if we look here, there's a cross product between the direction of the current and the radius. So that means that if we have a conductor here and the current's going into the board, and we have a radius here, then the magnetic field must always be perpendicular to both. So for a straight wire, we can infer some things without getting too wild on the math. So if it's going into the board and the other one's coming straight out, then the only choice this one has is to do this. But as we circulate the wire with our radius vector, you can see that the magnetic field has no choice but to circulate around a current carrying wire, as probably seen in numerous examples of metal filing experiments. So the magnetic field must be perpendicular to S and R, so it circulates a straight wire. An easy memory aid for this is the right-hand rule. Now, if you look in the books, they'll have right-hand rule number 1, number 2, number 3. I'm not smart enough to remember them all. I call it the right-hand rule, period, and I use context as into what makes sense and how to apply it. So let's have a look at how it works in this case. It works for solenoids and other things too. And in the 80s, when they decided to go with electron currents, you have to use the left-hand rule, okay? But we don't do that here because we're back to conventional universe. So, right-hand rule, and your thumb points in the direction of the current. And I'll just put underneath conventional currents. Okay? And your fingers will wrap around the wire in the direction of the magnetic field. So it is kind of funny to watch students write tests in this area because they're all doing this kind of stuff in the air, trying to figure things out as they work through the problems. It's kind of interesting. But this is a fine memory aid because if my pointer represents a current, I grab it with my thumb pointing the direction of the current, my fingers will curl around quite nicely. Okay, if we reverse the current, magnetic field reverses, same way, okay? So it's a rule of thumb that helps us sense directions for straight conductors. Now later on we get into solenoids and other types of things. You'll have different types of right-hand rules that will serve you in those things. And the geometries are different, and it helps you, and the common sense of the geometry will let you do that. Now I think that I'll take questions if they need or anything else, but I think that this is a reasonably good place to draw the line because we get into some fairly involved calculus here to find some fields before we learn something easy that allow us to do this without so much trouble. And so I don't know if a Friday afternoon is a good time to do that. So maybe we'll start things on Monday afternoon with some a little more intensity. Okay, thanks for watching. Hey, all right, so let's get to a little bit. So last day we started talking about the magnetic fields due to currents, and we just got started, and I talked about the magnetic field due to a straight wire, and I convinced you, I hope, that it is circulates the wire in the direction of the magnetic field. So I explained the right-hand rule and how we can infer what's going on, and this is all fairly straightforward. We can use the Biot-Savart law here that our movement along the wire crossed with the point perpendicular to that wire, that is where we're interested in the field, causes the magnetic field to circulate. So if the S is going into the board in this example and the R's are wherever you want, if you move the R around, it causes the field to circle. So around a straight wire for now, you get a circulating field pursuant to the right-hand rule and the direction of conventional current, not electron current, right? So be careful about that. All right, so with that, so I guess we can maintain this. We'll rub off this So I'm calling magnetism unit 5, if that matters to you. And then I might add a unit 6 for applications like what we call electromagnetism, when we get to induction and Maxwell and all that. And then interference and diffraction and so forth would be another one, just sort of to categorize, not that it matters that much. Okay, so this gets a little bit more complicated, which is why I didn't want to pick on it before. Right, okay. Now, to derive the magnitude of the magnetic field at R, we have to use the Biot-Savart principle. So what I did last day was simply just deal with the direction, but I never talked about how we would compute the magnitude, which is part of the fun. So if we have a wire here, and we're saying for now the current is traveling upwards, and we have a point here, which we're going to call R0, and we have some arbitrary location here, and this will be S, and this is our little ds here, and we have an R here. Okay. So we integrate dB along the line. So what you can notice here, of course, is the R, in this case, unless it's perpendicular, is going to be at an angle. So that's going to change this cross product a little bit. And so if we want to do the whole line, then we have this location A here, if you want, which is just where R0 lines up, so we can compute B at A to B at infinity, and then double it for the other half of the wire. So we have B is equal to 2 from 0 to infinity, 0 being A, of the dB, which is going to be equal to mu naught I over 2 pi, integral 0 to infinity. Of course, it was originally over 4 pi, but with the 2 here, you lose 1, right? Sine of theta over r squared ds. So obviously the integrand, we must revise the integrand. Now we know this because from our inspection over here, theta is dynamic, R is dynamic, and of course the actual movement along S is dynamic. But these are interrelated, and so we need to find expressions for sine and R squared that are related to S. Okay? So theta, R, and S are related. So if you're messing around with something like this yourself, and you get this, that would be the first integrand you could do, but the first question you say to yourself, do I have 3 independent variables here? And you know, if you don't know, well, okay, but that's a technical issue that requires refinement then. So at least you know what you don't know, right? But you have to ask that question because you want your integrands to be as simple as possible. And generally speaking, it's really simple. You say, well, okay, if I move along S, will that change theta or R? And you know, in this case, for example, the answer is yes. So then they're clearly dependent. And you're not dealing with an integral with more than one variable and, you know, more trouble than you probably want. So R is equal to the square root of S squared plus R naught squared. So that's going to help because R naught is a constant and S is part of our variable, so that's a good thing. And sine theta is equal to sine of pi minus theta, which is equal to R naught over the square root of S squared plus R naught squared. So cleaning this up then, so our equation becomes B is equal to the integral, mu naught I over 2 pi, integral from 0 to infinity of R naught over square root, I should know that, S squared plus R naught squared to the 3/2 power ds. So this integrand equals this one, but now we have it only in terms of S and constants, which is a good thing. And so you could theoretically move this R naught over here if you wish to do so. And so we get B is equal to mu naught I over 2 pi R naught. And then in here we have S over S squared plus R naught squared to the 1/2 power from 0 to infinity. And when you're all done, you get mu naught I over 2 pi R naught. Sorry, in this case it will be R. Actually, no, it's R naught. So the magnetic field due to either half would be, of course, trivially, so B field to a half would be mu naught I over 4 pi R naught. Now we can step it aside and say B of R equals mu naught I over 4 pi R if R is taken as the perpendicular distance from the wire. So if we have our conductor going into the board, okay, then our magnetic field at some R is inversely proportional to that radius. Okay, it's only 1 over R, not R squared or anything like that. And it's been done, Andy. I did it. Thank you. We can move now, understandably, to things like circular arcs of wire. star. This, if the curvilinear path is not circular, then the math gets complicated. I'm not saying it's elliptical or something, I'm just saying anything other than a circular arc where we can make certain assumptions about constant radii and so on, then it's not too bad. But if you get into interesting shapes, it's okay, but most probably you'll have to use a computer to get your answers. So we start off with these algebraic convenience symmetric cases to show you how we do it. And then the difference between that and more complex geometry is simply the complexity of the mathematics, not of the concept. And I think there's some strength in this. So here we have a center of curvature. We have our wire. And we'll say the current is traveling in this direction. So there'll be some phi here. And a specific R0 for the radius. And once again, we have the ds calculus thing, which we've done already. So let's see what happens here. So the R is perpendicular to ds for all s, ds, and r's. So it simplifies the math here because our cross product will be a product instead of complexity, so that makes it a bit easier for us. So then dB will equal mu naught I over 4 pi R naught squared ds. And ds is equal to R naught d theta. Okay? Because it's not necessarily a unit circle, so we have to scale it. So when we put this in for ds, we'll lose the square here. Hence, b then equal to the integral of db, integral from 0 to phi of, let's pull on here. Oh, we'll do it that way. Then we got the whole works, u naught I R naught, all of it over 4 pi R naught squared d phi, which then, of course, with some cancellations and pulling the constants out, we get mu naught I over 4 pi R naught, integral from 0 to phi of d phi. So that's pretty simple. So v then equals, as you might expect, mu naught I phi over 4 pi r, and we'll just, so here, of course, we have r is equal to r naught, when it's no longer a dynamic variable. Most people do it that way. And of course, remind you further that phi is in radians. So always somebody after a test like this who gives out a mournful wail when they realize their calculator is in the wrong mode. So maybe there's a test that you can do, some kind of Van Double theorem, extrema theorem that you can use to catch yourself under these horrifying conditions. Two parallel currents. So long wires with currents can exert forces on each other. Now, at first blush, I mean, we have magnetic field around both wires. We all know magnets can push against each other. Those are just magnetic fields. So it seems reasonable there would be some ability to do this. Let's see what happens. So we would have a case like this one. And this is IA and IB. And right now they're parallel. And we have a current. That's L, sorry. And we have a separation distance of some D. Okay. Now let's understand what the magnetic fields are doing. So B sub BA is the magnetic field on B due to the current in A. And vice versa. So BAB by vice versa. So that's our notation, okay? Now let us at wire B, BAB is equal to mu naught IA, all of it over, 2 pi D. And we know it's D because it's constant separation, parallel currents, right? Of course, that's not right. I knew that. BBA is what I meant to say. Here we go. All right. So the right-hand rule requires that the direction of BA at B is down. So let's convince ourselves of that. It shouldn't be too hard. Current magnetic field on B due to A. So we have our right hand rule here, thumb pointing direction of the current, field lines orbiting. So if you go out a certain distance, they're going to be going into the board right at the point of current B. We can compute the force on B due to A, which again we'll label consistently F sub BA. On a length L, okay, and that length L of wire B. So we're talking about how long B is. The magnetic field of A is what it is, however constructed. So FBA is equal to IB L cross BA. Here's a good example then of the current, two parallel currents, and how that actually works. Of course, we can then remind ourselves of the definition of this and get a more interesting equation, as we will do, I suspect. Since L is, of course, parallel with the current, is perpendicular to B sub A, and FBA is ILB. Now, also, and we'll make that BA. BA was equal to mu naught IA over 2 pi d. Right? So we could substitute this in here, and then we get FBA is equal to, this is IB here, so we're going to have mu naught IA IB over 2 pi d, and we need an L in there too. So let's look at the analysis of this direction. We said originally that FBA is equal to L cross B. These are the vectors here. So we've got B pointing down and L pointing this way, and it's L cross B. So the thumb is this way and B is down. That means the product, right, is pointing this way. So the force is towards the other wire. And the other wire will enjoy a similar force the other way. So this leads us to the conclusion that parallel currents attract. So FBA toward IA. So parallel currents attract, and anti-parallel repel.
Question?
Yes?
When you say BA, is that the field acting on A by B?
That is the field due to A anywhere. Okay, because it's completely general. Where did I put it here? Here. So, okay, so I said the field at B due to A, okay, but it really is just the field due to A anywhere you want. I'm just choosing this B here because we've got the D here as the argument, the distance being to that of B, okay? So anti-parallel repel. So that's, and I believe, I apologize, memory gets rusty sometimes, but I believe this is how we define the Ampere. So, because this is a sensible thing, you can measure this force. You know the currents, you know the distance, everything is there. Well, okay. We can say we know the currents, okay, what we think based on Ohm's law or something. But in the end, this force is a function of the product of these two. Everything else is sensible and measurable. So there's one place where we can actually measure these devices. And I'll show you one other one a little bit later. Do you remember, I don't believe I did any electricity with you guys last year, is that right?
Nope.
Okay, so one thing I'll show you in this unit is what we call a meter movement. So, of course, you're used to see a lot today with very digital type electrical meters, and that may be what you experience. But there's still the meters that have the needles on them, and it's a very clever device that's electromagnetic that is called a meter movement that allowed the initial sensing of electrical phenomena to be measured. And in many ways, it takes advantage of some of the things we're doing now. But we'll go a little further before we do that. Okay, something new now. It's called Ampere's law. In electric fields, we used Gauss's law to simplify the computation of electric fields if a Gaussian surface could be found whose geometry was known. Similarly, for magnetic fields, we use a concept called called Ampere's law. Integral of B dot ds is equal to mu naught I enclosed. So what this means now, and I'll write it down but just talk about it for a second, is you take a current, or however many currents you want to use, and you encircle them with a closed loop, an Amperion loop. And each of these currents is producing a magnetic field. And if you, these sum, okay, as you add them up around the Amperion loop, and it has to be a closed loop, which hence the ring integral, you can have this constant times the enclosed current, which is just the net enclosed current. So if you have one current going towards you and one away, the net current is zero, if they're the same magnitude, right? But if they're both going the same way or whatever, then it gets interesting. Now, the issue here, of course, is how do we choose our Amperion loops so that we can simplify the mathematics? Okay, so in this instance, B dot ds equals B ds if B is parallel to ds. So in effect, what you would like is to have the Amperion loop going the same direction, or at least as the magnetic field is. Okay, so if the magnetic field around a conductor is circular, then you choose a circular Amperion loop, right? And then you know at all times they're parallel, and you can just multiply. So it's the same kind of logic as we had with the Gauss's law and the Gaussian surface of having the area vector parallel with the electric field. So the area surface is thus perpendicular to it, which is a maximum, and then you get just a simple product, which isn't so bad. So this is the strategy, and I'm moving on it because we've danced with some things like this before. So let's first look at, consider the magnetic field outside a long straight conductor. So basically the calculation we did a few minutes ago was all kinds of calculus. So we'll have our current here, and the wire will go into the board. Okay, and so our magnetic field at some arbitrary distance is this. It's circulating. We know that from our cross product rules. So we can choose an Amperion loop anywhere here as long as it's enclosing the current. So because the magnetic field is everywhere here, it's not just where we drew the line. So it makes no difference. We can just draw an Amperion loop in yellow here. This is our Amperion loop. So let's just look at the ring integral of B dot ds equals mu naught I enclosed. Okay? So we've enclosed the total current that's currently flowing that we're interested in, so that's okay. Now, we're going to integrate around this loop here, and it's just going to be the perimeter, circumference, if you will. 2 pi r, right? So it's going to be B 2 pi r equals mu naught I. So B then is equal to mu naught I over 2 pi r. And we're done. Now, you can go back and use the integral 23 or whatever number it happens to be to solve such a problem, or you can do it this way with the same answer. Even more interesting, perhaps, would be the magnetic field inside the conductor. So this would be inside. We're assuming a steady current, steady uniform current. So in effect, at a consistent radius of the conductor, then the current density is the same everywhere, right? So we'll have our conductor, draw it bigger now, okay. Capital R, or R naught we'll say in this case. And we want an arbitrary location inside here. This is our Amperion loop. We expect the field to circulate yet again. There's no reason why it wouldn't. The Biot-Savart law kind of forces that. So ring integral B dot ds is equal to B times 2 pi r, where r is the radius of interest, right? And mu naught I is going to equal mu naught, but now we want to know the current that's enclosed by the Amperion loop will be the area here, okay? So this is going to be pi r squared. Now we have to scale this, so let's do this a separate way here. We'd have pi r squared over pi r naught squared times I being the total current, and now you're determining the fraction of the area, cross-sectional area of the conductor you're interested in. Clearly the pi's will cancel. Okay, so that put it together here, we got B is equal to 2 pi r, oops, that's what I want. B times 2 pi r is equal to mu naught I r squared over r naught squared. So let's finish it, and then I'll check my notes to see if I've made a mistake or not, but it seems pretty reasonable. It always does until you find the right answer, I suppose. So then we have B is equal to mu naught I r squared over r naught times, or divided by, sorry, 2 pi r. Okay, and so this r would be canceled with the square there, I guess. And so that's again the mu naught I over 2 pi, and it would be r over r naught squared. Now let's see if I get it right. It's a miracle. We write it typically mu naught I over 2 pi r naught squared, quantity as a constant, times the r. So as you move outward in the conductor, as you might expect, because the current increases, the magnetic field increases, and that is a linear function. So as you move out of the conductor, the magnetic field in the center of the conductor is 0, and as you move out, it increases up to whatever it would be at the surface. Solenoids. Just be a second, folks. Now, the magnetic field of a conductor is actually quite small, and we don't have to try very hard to see that. We take mu naught I over 2 pi r. Mu naught is 10 to the minus 7, whatevers. So if this is 1 amp, and you're, 0.1 meters away, say, then this is maybe, then the numerator is like 10 times 10 to the minus 7. You're still dealing with a micro Tesla. It's not a sensible field. It's not going to be able to do anything really for most applications in our situation. So the magnetic field due to a single wire is unimpressive. However, wrapping such a wire around a cord can cause the magnetic field due to each wire or each turn, let's say, to some. Of course, the current is the same throughout all of the turns. It doesn't change anything. But let's look and see what happens here. We take a small part of the coil and we'll say, well, let's get my diagram the same so I don't make too much of a fool of myself. Okay, so the top currents are coming out of the board towards us, right? And the bottom ones are going back in. So we have cut the coil down its longitudinal center, right? Now, the magnetic field for each wire, let's use the right-hand rule here. It's going to be, in this case, circulating like so. And then with the right this way, it's going that way. Now, I draw your attention to the spots in between the wires. Here it's going up, here it's going down. They cancel. And what we get instead is a magnetic field that encompasses all of them. Just by the geometry of a coil. And this leads us to right-hand rule number, forget these stupid numbers, the second application of the right-hand rule, okay? And again, it only makes sense, you can mix them up. We used the first version already. The second version is for coils. If you put your fingers in the direction of the current, okay, your thumb will point to the North Pole. So we get a North Pole here and a South Pole here. And be careful, you might, oh, well, sir, the field lines go from the north to the south. Yeah, okay, sure, but that's on the outside, not on the inside. Now, the magnetic field is quite intense in here because these field lines cannot cross. And they have to be crushed into that small space, so that gets to be pretty impressive. But the field lines on the outside can expand as far as the universe. Although it's not true, it's so much smaller than inside, we basically assume it to be zero. So let's have a look and see if we can figure out what the magnetic field is to the solenoid. So what might be magnetic field to the coil, or what we call solenoid. Okay. Well, we can use Ampere's law. Strangely, we'll use a square here. Okay. So I'm running out of colors. Let's see what else we got. Oh, we got some orange here. I guess that'll work. Or blue. Let's try orange. So we'll take a box here around, let's say, 2 of these coils, like so. And we're using a straight line. And we're going to label the corners, because we'll have to do 4 intervals, because we can't integrate around a sharp corner. Let me get my A, B, C, D. Okay. So we're going to have A, B, C, and D. Okay. And the length of this thing is some arbitrary variable h. Okay? So, do I have a second one? Second here. Doesn't matter. Okay. Well, yeah, exactly. Okay. All right. So, by Ampere's law, we've got the ring integral of B dot ds is equal to the integral from A to B of BH plus the integral from A to B, it's not B that way, B to C of B, we'll just say ds for now, plus integral from C to D of BH plus the integral from D to A of BDS. Now these two, we said the field in between is 0, right? So the field here will be 0, so that these integrals don't worry, we don't have trouble with those. So then we got the ones on those 2 to do. The inside is uniform. I'll put here at the center. So if we look at the field lines, this is of course too short a solenoid. You'd have hundreds of these things. So in the middle here, these lines are more or less parallel and are tightly packed. We have divergences here at the ends, which we don't trouble ourselves with for now. And B external is perceived to be 0. So, the B of the solenoid is equal to the integral of B ds from A to B, which is equal to let's get it right here, equals BH. And then mu naught I enclosed is equal to mu naught NH times I. So what does that mean? And we have to be careful with small n's because they will trick you in this business. So please be careful. We saw n last time was a number density, and usually these small n's are some kind of density thing based on the context of what you're doing. So you just have to slow down and really understand what they represent. Typically, the number of turns is a capital N. The number of turns per unit length, in this case, would be the lowercase n. So there's like a linear density here, okay? So for the box, you would have, in this case, 2 divided by some distance here, okay? And so what we have then is n, which is the number of turns per meter, times the number of meters. And you combine these two, you get big N. So big N equals NH. This is number of turns in H, length H. So what's interesting with the solenoid, and I'll finish this in a second, is not how many turns you have, but their density. And that surprises people sometimes, because we always get kind of lost on the number of turns. So then we would have BH is equal to mu naught N HI, and we lose the two H's, and you get B is equal to mu naught I times N. And again, N is number of turns per meter. Now it's per unit length, but we're using MKS, so we'll stick with that. Now this is, of course, an infinitely long solenoid, but we don't worry about such details. We say near the center. So very similar to the infinite sheet of charge, we simply say well away from the edge, or something like that, and these miserable edge effects do not have to be considered. So star, while not an infinite long solenoid, this expression is valid near the center. Now, if we consider, just for fun, the situation at the end here, either one, well, what do we know? Well, suddenly, our straight line here is no longer parallel to the field line. There's an angle here, so we've got some homework to do there. The field line here is clearly active. It's no longer 0, so we'd have some homework to do here with what is a straight line, which has nothing to do anymore with the shape of the field. And even if we assume that the field outside is more or less 0, we have trouble here and trouble there. So the calculation would be ponderous. And like I said before, the shape of these field lines are not some kind of de facto, ellipsoid or whatever. They're complicated, and they generally have to be computed. So at this stage of our education and this stuff, we stay away from the edges. Now we could take also a toroid and a toroid, of course, is a solenoid that's simply bent around upon itself. Now this is interesting because the density on the inside of the turns is going to be greater than the density on the outside. So a toroid is effectively a solenoid bent around in a circle. And so let's, we'll just draw one here. By inspection, the number density outside is less than the number density inside. We therefore expect a graduation of the intensity of B as we move out while inside. So the magnetic field of interest is inside the toroid. Outside is arguably negligible. Now, I'm sure if you had something nearby, you'd pick up something, but that's not what matters. So if we have an Amperion loop going around the inside here at some location, some arbitrary distance, whatever, in this case, it's a bit different because what does the Amperion loop circulate? If we draw it in there like that, it encounters all the coils. And so here, integral of B ds is equal to B 2 pi r, of whatever radius it is, okay, and mu naught I is equal to mu naught I times n, and all the, however many turns you've got around this thing. And so we just put this together, and we get mu naught I n over 2 pi quantity times r. Sorry, I misspoke. Times 1 over r. So inside a toroid, from inner to outer, the magnetic field is inversely proportional to that range. And so it's interesting when you consider tokamaks and other fusion containment devices. It's an interesting thing because you don't really have containment the way you think you do, because the magnetic field gets less as you move out. It's not a uniform field. We think, gee, okay, if I have the same field on both sides, I could keep this stuff in there. But that's not quite what's going on here. So this is, of course, one of the tricky businesses. Now, fusion power, of course, if you're doing it in a hot fusion situation, they're looking at about 100 million kelvins plus or minus for the plasma, and they're using, deuterium and tritium and all these and so forth. So the problem there is you can't put that in a pot because there's no material known that can take those kind of temperatures. So the only really way we can do it in this particular case is to confine it with a magnetic field and hope quantum tunneling and what have you does their job. Now that's got to be the biggest simplification in a week, but it does do the job. What else we got here before we're done? I have one more page and I'm going to finish it, folks. So we can make a video. So there's the toroid. I already mentioned the poles on this, but let's look at it a little differently. So a coil has a magnetic dipole, which I've kind of already alluded to. We found in the last day that tau is equal to mu cross B, where mu was the magnetic dipole moment of NIA. We get a current loop to rotate. But of course, what is a solenoid but a current loop, right? It's the same kind of thing. Now let's suppose we have our coil here. So we can have our magnetic field along the z-axis. We might say, well, what would be the field as we move away from that, along that axis? What would our magnetic field look like? So this is our z-axis here. So what is B of z? And we can kind of get away with it here because of the symmetry. We consider first a coil of one loop, just to make it easier. Then we have B of z is equal to mu naught I r naught squared divided by 2 r naught squared plus z squared to the 3 house power. Now, of course, we move away, then the distance here is significantly larger than the radius of our thin solenoid. So we can start making some assumptions here. We have to be careful though, but we can. Mind you, this is just equation, so you can stick that in somewhere and calculate. If z is bigger than r naught, so each of these greater thans you consider as an order of magnitude as a rough rule of thumb. So like 100 times greater kind of things, you know. Then B of z would be roughly mu naught I r naught squared over 2z cubed. So, which is, you know, kind of a waste of time, but and I'll say why in a minute. But let's suppose this is basically approaches 0, then this just cancels down to z cubed here. This stays the same. This basically vanishes too. So when you do these together, okay, you z cubed, and then you have 1 r naught left. So that's what's going on there. Although I guess they're not doing it that way. Interesting. Boy, that's really taking some liberties. Okay, well, whatever. The thing you'll find, though, is that this 1 over z cubed is fatal, okay? And your field drops off precipitously. as you move away from the coil. So this is really, you know, not really necessary. Also, B of Z is equal to mu naught over 2 pi of NIA over Z cubed. So this is R squared here, okay? And then you can, this is the linear density, so which is probably why they got rid of the R there. But again, there's a lot of approximating going on, so I wouldn't sharpen my pencil too strongly here on this one. But this leads, of course, to the meter movement thing, which is kind of cool too. But I don't want to take too much of your time. There's one line or two left here, I think, and that's it. I won't even bother. Okay. So, let's just see what the next one is here. So they'll begin induction. Okay. All right. Let me just do this other thing for a minute because it's related directly to this, and it's not an induction thing in any real way. So let's just do it now. If you have a current in a circuit and you wanted to measure the current or the voltage or whatever, and you want to use some kind of detection system, up until very recently, this is what we used. And I don't know, it's got to be 150 years old, something like that anyway. So what we do is, first we have a permanent magnet on either side. We'll have north, south, let's just arbitrarily choose them. Then we're going to put a coil here, like so, in which we'll put some wires around. And there's an axle that points out of the page, okay? So the axle is, so this thing can rotate like this, okay? And we'll stick on here some arbitrary location, a wand, and then we will connect the wire here to a terminal, and the other wire over here is another terminal. And when a current passes through this will energize. And this is designed to energize in such a way that this will be north and this will be south if it's connected properly. If it's connected wrongly, it'll slam this way. Now, I haven't finished this yet because right now, this current, these bearings that hold this are very, very fine, very, very low resistance bearings. You'll often see meters in those days with, 7 joules or something like that. They mean that based on the movement apparatus. Now, as it is, if I energize this thing's going to slam over here. That's going to be it. And we're not going to get anywhere. So instead what we do is we put a watch spring in here. I'm going to get the right direction. So a second here. Yeah, that's the way. So as the meter rotates like this, it winds the watch spring slightly. Now this watch spring is, the torque is a function of the angle. And this torque is linear to the angle in radians. So what that means is just like a compressive spring, as you continually rotate it, the force, the torque, if you will, gets increasingly greater. The torque of this rotation here is a function of the current. When this torque is what it is. For a steady current, it's going to be some value. So this thing will rotate around until the torque of the spring balances with the electromagnetic torque, and then the wand points at the location of the scale you want it to. So for a given current, you have torque due to I is some value. And then the torque to the spring opposes. It will balance. And the wand points to the value on the scale. So you would have above here, this is the part you get to see. The guts are hidden, okay? And you would have your scale here. And one of the things interesting with wands is that you want to make sure you're looking at them straight on. So what you'll notice in some of these is they have a mirror, like so. And the mirror is there. If you see two needles, then you're off on an angle. And because we can't have any friction, the wand lies above the scale, doesn't scratch it, doesn't touch it. So if you're seeing two needles, you know you haven't lined up and you've repositioned yourself so you see only one, and then you'll know that the reading you're seeing is correct. Now just another point here, just to finish this. This is the kind of stuff no one's going to tell you. So let's suppose we're measuring current. So an ammeter case. So we have a circuit like so, resistor, ammeter, resistor, back around. We want to measure the current. Now the current could be just about anything, right? But this is very delicate. You can't drop it, you can't throw it around, you can't put amps or currents, or this will just turn into molten plastic and copper. If you do, this is microamps. It's very, very fine. If you see these things, the hair, the wire on these coils is just gossamer thin, okay? So the meter movement is a microammeter. So the device that we use to access this has to deal with the fact that the current can be whatever in a circuit. We must then divert, in parenthesis shunt, most of the current around the meter. So what we do in here is we have, so the expanded view here is the wire will come in, and then we have, here's our meter movement doing its thing, and here we have a resistor in parallel, like so. And we want the current to flow through this guy. And there'll be a parallel portion that flows through here that we can use to sense. We want to send most of this through here. So this is what we call our shunt resistor. So our shunt is less than the resistance of the meter. So shunt resistors often are misunderstood in meters. If you look at them, they look like wires, or even big wires sometimes, or coiled wires, because they're designed to have low resistance, which is a wire often cases, and which will take a proportional amount of the current away and preserve the meter. If you have a meter with multiple ranges, it just means that when you rotate the switch, you're choosing whichever resistor makes sense for the range you want. If it says 10 amps, that means the maximum safe measurement is 10 amps. Now, I've prohibited you from using the ammeter function because people don't know what they're doing and will choose the wrong one and it'll blow the fuse. We usually put a fuse in the meter to student-proof them as well, and we generally underfuse the meters as well, just to be safe. But most of the time, these meters are multiple, or what we call multimeters, which means they can measure not just current, but most people don't want to have an ammeter and a voltmeter and an ohm meter and all that kind of separate equipment. It's expensive. So for a voltmeter, it's the opposite. And even in this case, we don't want this thing to subtract from this circuit, right? That's important. And with this being so low, it's not going to modify the current materially from those two resistors. But on the other hand, we have the same circuit here again. Now we want to know, say across here, what is delta V? Now, by Ohm's law, V is equal to I times R. Now, here's the point, is that we can choose our resistors very carefully in the meter. The resistance of the voltmeter, okay, as the current flows it, we have very precise resistors in there. We'll know exactly for a particular range. So, for a given range, the resistor is such that V max reduces I max, because the meter movement is still measuring current. It always measures current, but we fake it out. Okay, so what will happen here is you've got your test lead, and then depending on what you're choosing, we have a resistor that's chosen, R, and then we have our meter movement, and then it goes back around again. And so what happens now is this heavy-duty resistor limits the current. If you choose a low scale, what you shouldn't have, say the voltage here is 10 volts and you put a 1 volt scale, then the current will be too high and the meter will slam over. And you have to switch it. Now you can't do that without care or the meter will be damaged, but you can get away with a little bit. And then whatever it reads here, now this current here is small. So when we have our circuit here, the current is flowing through here like this. If this is a kilo ohm resistor or whatever, and this thing is 50 mega ohms, the amount of current flowing through here is irrelevant, and it's not going to materially affect the performance of the circuit. So the objective, of course, is the act of measuring is not to change materially the circuit, and that you can do it fairly efficiently. So ammeters are the biggest pain, so oftentimes we use the voltmeter and just tap a circuit, boom, 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 and see what's going on. And that's often done. And just for completeness, I'll do it over here for measuring resistance. In this case, you have a resistor that's not connected to a circuit, and you have your probes attached here. But in this case, the meter has a battery in it, which I changed last time in many of them, as you know. Now that battery runs the electronics in those meters as well as this. But then you have a case here now where we know the power supply, okay, and there's a resistor. So the current's going to be what it is. So now we can choose other, so for example, if we short the two terminals together, we're going to get a maximum current. Okay, so what happens in this case is the scale reverts to an opposite polarity. So over here is 0 ohms, and over here is an infinity value. And what you get is it's 1 over, so R is equal to V over I. So the scale is proportional to 1 over the current. So when you see these ohm scales, so there'll be a resistor here for safety and stuff like that, but you get this kind of thing. And so what happens is this thing will go back and you'll see the scale, and it's a 1 over I relationship. Now, we do it in ohms, so you don't know what it is, but it's a function of what the battery voltage is, which is often 1.5 volts or something like that. And this gives you, but you don't know that, you just read the scale, right, because that's what you do. So that's why these analog meters have so many scales on them. They're not only for potential, current, resistance, and other stuff maybe, but also for multiple scales of the same. And that makes the meter a very, very useful multiple tool. Now, in my case, I use both kinds. There are cases when analog meters are really useful, and there's cases when digital meters are really useful. Sometimes an analog meter where the needle moves a little bit like this and you can see what's going on can be really useful. Whereas a digital meter will just, the numbers will be changing in a way you can't follow. So in other times you really want to know what the voltage is to 2 or 3 significant digits, which is something that an analog meter is not very good at. So, you know, if you're just amateur playing around, you know, and you've got, say, $1,500, having both of those is probably worth it, or you inherit one from Uncle Wilbur or something like that. Okay, everybody, that finishes up the magnetic fields due to wires and this extra little bit. And that'll end this particular unit, and we'll begin with induction on Thursday.